So now I want to continue where I left off 4.5 and 4.6. I want to show you more examples about graphing functions. Example 4. How do I graph the rational function f of x equals x squared plus 1 over x squared minus 4? So first, domain, again, is all real numbers except where the denominator equals 0. So x equals plus or minus 2, so it's negative infinity to negative 2, negative 2 to 2, union 2 to infinity. Okay, so all real numbers except 2 and negative 2. Okay, and the intercepts, x-intercept, we can find by setting y equals 0, never, because the top cannot be 0, it's x squared plus 1. If you put it equal 0, you get imaginary solutions. Y-intercept, when x is 0, y is negative 1 over 4. So it crosses the y-axis at negative 1 over 4. Alright, now for asymptotes, we have we also have symmetry about the y-axis. It's an even function because f of negative x is going to equal exactly f of x. If you put a negative in there, it's going to square it, it's going to disappear, the negative. Okay. Vertical asymptote, x equals plus or minus 2. Horizontal asymptote, as the limit as x goes to infinity of f of x equals x squared over x squared, which is 1. So we have a horizontal asymptote, y equals 1. Okay, then we can do critical values. So we're going to find the derivative. So f of x equals x squared plus 1 over x squared minus 4. The first derivative, you know, a lot of these details are not in my notes, so you might want to write them down. Or, you know, you have the video, so f prime of x, so you do the bottom times the derivative of the top minus the top, which is x squared plus 1, times derivative of the bottom squared. So if you work it out, you get 2x cubed minus 8x minus 2x cubed minus 2x, which is negative 10x over x squared minus 4 squared. So to find the critical values, we say f prime equals 0 or undefined. Well, you can see f prime is undefined when f is undefined, so it's not going to be a critical value. F prime equals 0 when the top equals 0, so that means when x equals 0. So this is the only critical value. So it's the only candidate for relative extrema. And then we do our chart, but remember the domain is not all real numbers, so we're going to have to work that out. So negative infinity to negative 2, and then negative 2 to 0. Negative 2, it's undefined there, so we put that. So to remember that it's undefined. And 0 to 2, it's also undefined at 2. And then to infinity. We pick a test value within each interval. Negative 1, 1, and 3. We plug it into the first derivative equation. All we care about is the sign. So if we put negative 3, that's positive. That's positive, so it's positive. We have positive, that's positive, so it's positive. You have negative over positive, and then negative over positive is negative. F is increasing, decreasing, decreasing. So there's a relative max at 0. If you plug it in, that's the point of y-intercept, by the way. Okay. So now we're going to do the second derivative and points of inflection. So the second derivative is going to be, we take the bottom times the derivative of the top minus the top times derivative of the bottom, so 2x squared minus 4, then times 2x, x squared minus 4 square, which is to the fourth. So look, I can make things easier. I can divide x squared minus 4 from every term. This would be 1, and this would be 3. So the second derivative would be negative 10 times x squared minus 4, which is negative 10 squared plus 40. And that's gone. You have 4x times 10x. 4x times 10x is 40x squared, which would be 30x squared plus 40 over x squared minus 4 to the third power. So the second derivative is never going to be 0 because that's positive, and it's undefined where f is undefined, so no points of inflection. There's no candidates for points of inflection. Okay, so but we still have to look at concavity based on the domain, which is negative infinity, negative 2. It's undefined there, negative 2 to 2. It's undefined there, 2 to infinity. A test value, and then the second derivative, and then the function, how it behaves. The second derivative at negative 3, I got positive. You can check my work, negative, positive, so concave up, down, up. I mean, we have points of inflection there? Of course not, because the function is undefined there, okay? No points of inflection, but we know what the concavity is gonna look like. We did the intercept, we did the asymptotes, so now we can graph it. We have vertical asymptotes and horizontal asymptotes. We have vertical asymptotes at x equal 2 and at x equals negative 2. A graph may never ever cross its vertical asymptote because it's undefined there, but it may cross its horizontal asymptote as we have seen before. Okay, and it has a relative max at negative 1/4. Okay, so it's concave up from negative infinity to negative 2. I'm looking at there, concave up, so it can't be here, it has to be there. And it's concave down between negative 2 and 2, and it's increasing to 0 and then decreasing from 0 to 2. That's how we know concave up and increasing, concave down, decreasing, concave down, and then concave up and decreasing after 2. Okay, so that gives you a great graph. And let's do have two more, a polynomial and a trig graph. Okay, doing a lot of graphing so we can have a lot of examples to look after. So sketch the graph of f of x equals x to the 4th minus 8x cubed plus 18x squared minus 16x plus 5. So since it's a polynomial function, its domain is odd real numbers. And the intercepts, the y-intercept is at 5. X-intercept is where we have to do the work. Remember, we did zeros of polynomial function. We used rational zero theorem. We used synthetic division to find zeros and then factor it. So that's what we're doing right now. It's a lot of work, but it's okay. Plus 5 equals 0. So the rational zeros, p over q. P is 1 and 5. Q is 1. So p over q is plus or minus 1. But to narrow down the option, we punch it in the calculator. So we don't have to work blindly. X to the power 4 minus 8x cubed plus 18x squared x to the 4 minus 8x cubed plus 18x squared minus 16x plus 5. Graph it. So it looks like we have a 0 at -1 and then 2, 3, 4 at 5. Let's check. At -1, no, we don't have a 0 -1. At 5, yes, we do have a 0 at 5. Let's go back to the graph. Oh, at 1, I'm sorry, what am I saying? And what's interesting, if you see how the graph behaves at 1, it hugs the x-axis at 1, whereas at 5 it goes through. So that tells you it's an odd multiplicity, but it's more than 1, like 3. So there's going to be 3 times the 1, and then 1 time for the 5. It looks like that. Okay, it looks like that, which makes sense because they have to add up to 4 zeros. But let's check. So it looks like 1 is a 0. So let's divide by 1. So we get 1, -8, 18, -16, and 5. We drop the 1. 1 times 1 is 1. The -7. 1 times -7. 18 plus -7 is 11. That's -5. -5. Remainder is 0. Constant x squared, x. So we did all this in college algebra. So 1 is a 0, that means x minus 1 is a factor, so f of x is going to be x minus 1, and the other factor is right there. Now we can either, because we need to factor it more to get all the zeros, so we can either use 1 again. It looks like 1 has an odd multiplicity of 3, or we can do 5, because 5 is also a 0. It doesn't matter, but now we're going to divide it by that. So 1, -7, and -5. If I divide it by 5, drop the 1, that's 5, that's -2, -10, 1. So times, add. So again, 5 is a 0 as it looks from the graph and the chart. Constant x squared. So now let's go back here. We already got x minus 1. 5 is a 0, x minus 5 is a factor, and there's the last term. And as we predicted, x equal 1 appears 3 times. If you factor x squared minus 2x plus 1, you get x minus 1, x minus 1. And you can see why the graph does what it does at 1. So there's x equal 1 with multiplicity 3 and x equal 5 with multiplicity 1. Those are the x-intercepts or the zeros of the function. Okay, so we got those. Then, so we have no asymptotes. It's a polynomial function. Then we're going to talk about relative extrema and the first derivative. So let's the first derivative. 4x cubed minus 24x squared plus 36x minus 16. So to find the critical values, f prime equals 0. It's never undefined. It's a polynomial. So that means 4x cubed minus 24x squared plus 36x minus 16 equals 0. You can see we can divide the 4 to make it lighter. 6x squared plus 9x minus 4 equals 0. And if you put it in your calculator, you can see that 1 is a 0. So let's divide by 1. Just like we did in the original one. Drop the 1 down. 1 times 1 is 1. If you forgot synthetic division, I have a handout. It's posted on D2L under the handouts. It's -5. 1 times -5 plus 9 is 4. So 1 is a 0. So x minus 1 is a factor, and this is my other factor. X squared minus 5x plus 4. So this factors into -4, -1. So we have x equals 1, x equals 4, and x equals 1 again. So these are the critical values. Then we make our chart to see where it's increasing and where it's decreasing. 1 to 4 and 4 to infinity. A test value, we can pick 0. Between 1 and 4 we can pick 2, pick 5, the first derivative. We plug it away into the equation of the first derivative right there. You have a calculator, use it, so you get a negative, a positive. So the function is decreasing, there's a relative min at 4, and the y value, we plug it in, we get negative 27. So the function is decreasing from negative infinity to 1, then decrease again from 1 to 4. It has a relative minimum at 4, negative 27, then increases again. Concavity. So we do the second derivative for concavity and points of inflection. So the second derivative is going to be 12x squared minus 48x plus 36. It's quadratic, so we don't have to do any synthetic division. We can pull the 12 out. That's 4 plus 3. This is x minus 3, x minus 1. So we have two candidates for points of inflection, 3 and 1. So we do negative infinity to 1, 1 to 3, 3 to infinity. We pick a test value between negative infinity and 1, between 1 and 3, and then that, plug it into the second derivative. All we care about is whether it's positive or negative. So positive, negative, positive. Concavity is up, down, up. So we have a point of inflection at 1. The y value is 0, and we have a point of inflection at 3. The y value, again, where do I got my y values? All the way back into the equation. Okay, that's where we plug them in. And then if you graph it, again, you can see we already know what the graph looks like. It has, so I'll do 5 because we need bigger units, 10, 15. All right, so here I'm gonna do 1, 2, 3, 4, 5. And then negative 5, 10, 15, 20, 25, 30. So we have an intercept at 5. It's decreasing, concave up. And then it does some hugging at 1, 0. Remember, it's decreasing, and then it decreases again to 4, negative 27. That's our minimum. So concave up, then it switches concavity to down. Then it switches concavity again at 4, right? No, at 3. So right here it switches from down to up again, and then up all the way, and then it hits the x-axis at 5, 0. It's an x-intercept, and concave up. Okay, one more, which is going to be about trig. I haven't showed you any trig function to graph, so that's what I'd like to show you. So how do I graph f of x equals negative x plus 2 cosine x over the interval from 0 to 2 pi? Well, obviously the domain here is 0 to 2 pi. Right? That's what they're telling us to do. Although otherwise it would be all real numbers, but here they're restricting that. And to find the x-intercept and the y-intercept, the y-intercept is the easier one here. When you do x equals 0, you get y equal negative 0 plus 2 cosine 0. That's 2 plus 0 is 2, so 0, 2. The x-intercept, you're going to have to do it with the calculator. Okay, because it's not easy to do that, without a calculator. I'll show you when we graph it. Okay, it comes out to be 1.03, roughly. All right. So that's it. So there are no asymptotes. It's cosine, and then the critical value. So we find the first derivative. Derivative of x is negative 1. Derivative of 2 cosine x is minus 2 sine x equals 0 or undefined, but it's not undefined. It is a sine curve, so sine x equals negative 1/2. So if you look at the unit circle, it's at 7 pi over 6 and 11 pi over 6. Those are the critical values. So we're going to see whether or not they are points of maximum or minimum. So remember, we don't do negative infinity, the domain is 0, so we start at 0 to 7 pi over 6. 7 pi over 6 to 11 pi over 6. And then 11 pi over 6 to 2 pi. That's the domain, okay? We pick a test value, we plug it into the first derivative, and then we see the graph. So you have the unit circle, you can pick any test value from 0 to 7 pi over 6. You can do pi 2, from 7 pi over 6 to 11 pi over 6, 3 pi over 2, and then 11 pi over 6 to 2 pi. You can pick any number in there between 11 pi over 6 and 2 pi. If you're not sure, just figure out what these values are. 11 pi over 6 and 2 pi, because there's no specific value on the unit circle, because these are the same numbers, I mean close to each other. So between 5.76 and 6.28, so we can pick 6 radians, okay? F prime, you plug each one in there, you get negative, positive, negative, so the function is decreasing, increasing, decreasing, so we have a relative min, a relative max. At 7 pi over 6 we get the y value, and then at 11 pi over 6 we get the value by plugging them in. I got negative 5.4 roughly and negative 4, again by plugging those values into the calculator. So then we're going to do concavity and points of inflection. The second derivative is negative 2 cosine x equals 0 if x equals pi over 2 and 3 pi over 2, because this means sine x equals 0 over negative 2, which is 0, and that's where these came from. Again, we make a chart, 0 to pi over 2, pi over 2 to 3 pi over 2, and then 3 pi over 2 to 2 pi. It has value, second derivative, concavity. So we pick pi over 4, we pick pi, and then we pick 11 pi over 6. You have the unit circle, pick one value there. Negative, positive, negative second derivative, concave down, up. So we have a point of inflection, a point of inflection. Pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2. And then the graph, you can do the graph by hand and then check on your grapher between 0 and 2 pi. Remember we had at 0 it's at 2, the y-intercept, and then at pi over 2 it's negative pi over 2, that's where it changes concavity, pi over 2, negative pi over 2. And then it changes concavity at 3 pi over 2 with negative 3 pi over 2. And then it has a relative min at 7 pi over 6. So pi over 2, 2 pi over 2, 3 pi over 2, 2 pi over 2, 3 pi over 2, and then pi over 2 is 3 pi over 6, 4 pi over 6, that's 6 pi over 6, and then 7 pi over 6. So at 7 pi over 6 we have 11 pi over 6. So basically it's gonna look like this, and then at 7 pi over 6 it's going to have a minimum, and then it has a at 11 pi over 6 negative 4, and then it stops at 2 pi. So this is the relative max, this is relative min. Sure, you can do that. Okay, and that's it for 4.5 and 4.6. Next is going to be optimization, which is 4.7.